We can send probes to the outer edges of the solar system, and our telescopes can see galaxies billions of light years away. Yet the 6,400 kilometers directly beneath our feet remain entirely opaque and physically unreachable. To map the interior, we rely on forensic seismology. By listening to the faint vibrations of distant earthquakes, using instruments like these early 20th century seismographs, scientists slowly piece together the structure of the deep Earth. Pioneering researchers like Inga Lehmann tracked two distinct types of vibrations: primary compression waves and secondary shear waves, as they bounced and bent through the planet's internal layers. Their work gave us the classic multi-layered model taught in schools for decades: a rocky crust, a flowing mantle, a liquid outer core, and at the very center, a dense, rigidly solid inner core made of crystallized iron. It all hung together neatly, explaining the basics of our dynamic planet. But as our global seismic monitoring network became more sensitive, we began to detect glitches in that simple model. Modern seismic networks are picking up contradictions from the inner core that defy the rules of basic material physics. This diagram shows primary waves, or P waves, traveling through the core. They zip exceptionally fast from pole to pole, suggesting a rigid crystal lattice aligned with the planet's spin. But secondary S waves tell a different story. They propagate sluggishly and lose energy rapidly, behavior unexpected from a stiff, solid iron structure. To quantify this, geologists use Poisson's ratio, a metric that compares a material's resistance to being compressed against its resistance to being sheared. A typical solid has a Poisson's ratio around 0.2 or 0.3. Earth's inner core sits at roughly 0.45. For a material that should be stiff crystalline iron, it mathematically behaves like rubber. It is inexplicably squidgy. Scientists first looked for a chemical explanation, hypothesizing that the iron crystal lattice was alloyed with lighter elements like carbon or sulfur to soften the structure. However, molecular simulations show that even high concentrations of these elements cannot slow down S waves enough to match the seismic data we see in the real world. Another theory suggested the core is fragmented into grains, with microscopic membranes of melted iron acting as a lubricant between solid chunks. The problem is that a fragmented core becomes too goopy. It would absorb even more energy than we observe and would struggle to maintain the global alignment needed to explain those fast pole-to-pole P waves. This leaves us searching for a state of matter that is simultaneously a highly structured rigid solid and a fluid. This is the superionic state. It's a phase of matter where one element forms a rigid geometric crystal lattice, while a second, lighter element flows rapidly through the empty spaces of that grid like a liquid. At the center of the Earth, the extreme heat and pressure allow iron and nickel to form the rigid cage, while lighter elements like carbon detach and move freely through the structure. Molecular simulations of this superionic iron-carbon alloy returned a Poisson's ratio of 0.43. This is an almost perfect match for the impossible seismic data recorded by our sensors. The simulations are compelling, but confirming this requires recreating the conditions of the center of the Earth inside a laboratory. To do this, researchers used a light gas gun, a device that uses hydrogen or helium to accelerate projectiles far beyond the speeds possible with traditional explosives. By slamming a projectile into an iron-carbon target at Mach 20, they generated the immense shock pressures and temperatures needed to momentarily force the metal into a superionic state. They used specialized lasers to read the surface vibrations of the shocked metal, mimicking the way seismologists read the vibrations of the Earth. The experiment worked. The laser data revealed that superionic iron exhibits the exact same shear softening and high Poisson's ratio found deep within the planet. Earth's inner core isn't a static sphere of solid iron. It's a superionic environment where a rigid metal cage contains a liquid-like stream of lighter elements. This directional flow of carbon along the rotational axis adds a new variable to the fluid dynamics of our interior. This internal movement may actively participate in the geodynamo effect, providing an additional boost to the magnetic field that shields our atmosphere. Whether we are mapping the edge of the visible universe or the center of our own planet, the same principles apply. We interpret the faint vibrations reaching us from the dark, and when necessary, recreate those extreme conditions ourselves at 20 times the speed of sound.